Okay, so now the next question we need to answer is how do we draw Lewis structures for a molecule? So the first thing we're going to look at is carbon tetrafluoride. It's a really nice example. So CF4. The first step is to calculate the total number of valence electrons available for bonding and divide it by 2 to determine how many bonding pairs are available to build your Lewis structure. So I look at the periodic table, and carbon is in group 4, and so it has 4 valence electrons. Fluorine's in group 7, and so each fluorine has 7 valence electrons that it can bring. So since there's 4 fluorines, we have to do 7 valence electrons times 4. So from the fluorines, we get 28 valence electrons to play with. We can add those together, the contribution from the carbon and the contribution from the fluorine, which gives us 32 excuse me, valence electrons to build this molecule. And if we divide that by 2, that gives us 16 bonding pairs. Next step, we need to determine which atom is the central atom using the following guidelines. The atom with the lowest electronegativity is the central atom, almost always. The central atom is often written first in the formula. And the last thing to keep in mind is that hydrogen and fluorine are never, ever, 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 ever the central atom, ever. Okay, so in this case, CF4, carbon has a lower electronegativity than fluorine, and it's written first in the formula, and fluorine can never be the central atom. Therefore, carbon must be the central atom. So now that we know our central atom, we can move on to the next step, which is to start to build this thing. So we're going to use one bonding pair to bond each outer atom to the central atom. Now recall that a line represents a bonding pair. So this line stands for 2 electrons. You could draw 2 dots, but that's a lot of effort. If you prefer drawing each electron individually, please do so. I like to use lines. So here's our bonding pairs. We're going to use a bonding pair to attach each thing to the central atom carbon. So that means I've used 4 bonding pairs out of the 16 I had available. So I have 12 bonding pairs left over. So that takes us to the next step, which is to start to add bonding pairs to my outside atoms. So we want to fill the non-bonding electron pairs, so the lone pairs, around the outer atoms so that each outer atom has an octet. So that would be 4 bonding pairs, or 2 electrons if the element is hydrogen, right? But fluorine needs 8. So I'm going to take my remaining 12 bonding pairs and put them around the outside of the fluorines so that each fluorine thinks it has 8. So this one has 2, 4, 6, 8. This one has 2, 4, 6, 8. The one on the bottom, 2, 4, 6, 8. And the one on the right side, 2, 4, 6, 8. At this point, I want to also look at my central atom and make sure that it has 8 valence electrons also. And this carbon does. It has 2, 4, 6, 8. So everybody's happy. Everybody thinks they have 8 valence electrons, and there was much rejoicing in the world of chemistry. So there it is. You're done. However, there are some circumstances where it doesn't work out quite this nicely, because of course. And so we have to consider this question: what happens if we run out of electrons before we satisfy the octet rule for all of the atoms involved? Luckily, we have a contingency plan. So let's look at another example so that we can understand what that plan is. So if we have carbon dioxide, and we looked at carbon dioxide earlier, we can say, all right, carbon brings 4 valence electrons to the party, plus each oxygen brings 6 valence electrons. So 4 plus 2 times 6 gives us 16 valence electrons, which means there are 8 bonding pairs. Carbon is a central atom because it has a lower electronegativity than oxygen, plus it's written first in the formula. Then you can see we have our third step, which is to stick the other elements to the central atom. So we have 2 bonding pairs holding the oxygens to the carbon. So out of our 8 bonding pairs, we've used 2, so we have 6 left. So we're going to put the 6 we have left around the outside atoms first. We don't put them on the central atom first, we put them on the outside atoms first. So 1, 2, 3, 4, 5, 6. So we've used all our bonding pairs, we have no bonding pairs left, and now we're going to evaluate, is everybody happy? So oxygen has 2, 4, 6, 8 electrons. Oxygen is happy. The other oxygen, 1, 2, 3, 4, so 4 times 2 is 8, has 8 electrons, 4 bonding pairs. It's happy. Carbon, on the other hand, only has 2 bonding pair, which means it only has 4 electrons. So carbon thinks this deal sucks. Carbon is like, I am not stable, I do not like this, I need more electrons. So because of this, we have to kind of double share our electrons. And we're going to make a double bond to do that. So this is what that would look like. We would move one of the lone non-bonding pairs from the outside atoms to be shared between the central atom and an outer atom. So I took a pair away from oxygen and just had oxygen share it with carbon instead of keeping it to itself. Same thing on the other side. I had oxygen share a second pair of electrons with carbon. So now oxygen still thinks it has 2, 4, 6, 8 electrons. This oxygen still thinks it has 2, 4, 6, 8 electrons. And carbon thinks it has 8 electrons. So everybody's happy now. One thing that you might think about is that you could, theoretically, put 3 bonds on the left-hand side and keep 1 bond on the right-hand side, right? Because carbon would still think it had 4, and the oxygens would still be satisfied, but you really don't want to make multiple bonds unless you have to, and making a triple bond is a lot more intense than making a double bond, and our molecules tend to like to be symmetrical because that's usually the most electronically stable thing, is to be symmetrical. So that's something that I always think about when I'm drawing Lewis structures, is like, how can I make this symmetrical so that it's like balanced? Because then that's the most stable thing for the molecule. Okay, so what I want to do is walk you guys through some examples from your worksheet, and then once we've done that, you're going to be turned loose on those on your own. So bear with me, I'm going to switch to that screen, and then we will do some examples together. All right, this worksheet has for you the steps that we just talked about in the notes listed out for your reference, and we're just going to do a couple examples together. So first example, SO2, there's no charge on this. It's not a polyatomic ion of any kind. It's just sulfur dioxide. And the first thing we want to do is think about how many electrons each element brings to the party. So we'll find those guys on the periodic table. Sulfur and oxygen are both in family number 6. So they each have 6 valence electrons. So we'll have 6 plus 2 times 6 for the oxygen gives us 18 electrons. And so that's going to be divided by 2, gives us 9 bonding pair. Next thing I want to do is think about which one's going to be in the center. Sulfur is a row lower than oxygen on the periodic table, so it's less electronegative. So sulfur is going to go in the center. It also is written first, so that's another clue that we can look at. Then I'm going to use a bonding pair to attach each outer atom. So that was 2 bonding pairs, so we have 7 left. I'm going to start putting my bonding pairs on the outside atoms first, and then if I have some left, I'll put it on the central atom. So 1, oh dear. 1, 2, 3, 4, 5, 6, 7. Now I have to make sure that everybody has a full octet. Left-hand oxygen, 2, 4, 6, 8. It's happy. Right-hand oxygen, 2, 4, 6, 8. It's happy. Sulfur in the middle, 2, 4, 6. Sulfur is not happy. Sulfur thinks this is bogus. So we need to make a multi-bond so that our sulfur can also have 8 valence electrons. So I'll take one of my lone pairs off an oxygen. I'll just do this one. And I'm going to put it to be shared between the oxygen and the sulfur. So now oxygen still thinks it has 8. Sulfur thinks it has 8. And the right-hand oxygen hasn't changed at all, so it still has 8. You can definitely put the double bond on the other side. So you could draw this like so, and that's totally acceptable as well. When you have 2 kind of similar structures like this, we call them resonance structures. Resonance structures. Because they are really equivalent in the eyes of the chemistry law, and they are both equally correct. So there's that. Let's talk real quick about what you do if you have something like HSO4. Like where do we put the H, and what does it mean that we have this 1 minus on this hydrogen sulfate? Like, what the heck? So we'll do hydrogen sulfate, just kind of in the middle here. First, tally up all our valence electrons. Hydrogen brings 1, sulfur brings 6, each oxygen brings 6. So that's 1 plus 6 plus 4 times 6. Then we have this little bonus electron, so we'll do plus 1. You should never have an odd number of valence electrons in your count, because then when you divide by 2, you get like, 1.5 bonding pairs, and that doesn't even make sense. So that's why some of these charges, these little extra electrons end up popping. Okay, so then we'll total that up, and that is 32. So 32 valence electrons divided by, oh, whoops, didn't mean to do that. Divided by 2 is 16 bonding pair. Central atom, lowest electronegativity. That's going to be sulfur plus hydrogen, can never be the central atom, so we don't have to worry about that idea. So sulfur is the central atom. I'm going to stick each of the oxygens on there. And so that's good. And then we're kind of in this weird situation of like, well, where should we put the H? You'll notice sulfur already has a full octet from attaching the oxygens. So we're going to put the H on an oxygen. And this will always be the case, you guys. You always put hydrogens on an oxygen, okay, if there's an oxygen available. All right, so now we're going to go ahead and fill out the rest of our bonding pair.